now we can start. Today, we will host the last session of our workshop. And the workshop is the fourth workshop on proximity perception in robotics. And this year's topic is increasing safety for human-robot interaction using tactile and proximity perception. So the idea is this year also to provide a bridging towards the industry. And therefore we have in our extra session 3 speakers, of which 2 are invited speakers and 1 is part of the PhD forum. So first of all, we have today Dr. Peter Heiligensetzer from Kramer-Botigglio, and then we have Francesca Palermo from Queen Mary University of London, and then we have Professor Rebecca Kramer-Botigglio. And today I'm happy to introduce our first speaker, Dr. Peter Heiligensetzer. And he finished his PhD in robotics at Karlsruhe University, Karlsruhe Institute of Technology, about tactile and capacitive proximity sensors. And he also worked at KUKA and later founded the company Kramer-Systeme, which focuses on technologies regarding human-robot collaboration, as the name also says. And Kramer-Systeme offers many interesting and advanced solutions for industry applications with close human-robot interaction and physical contact with humans and robots. For example, hand guidance based on force controls to increase the intuitiveness of the teaching processes. And they also offer a tactile and proximity sensing skin that covers the surface of industrial robots to enable human-robot interaction functionality. He's also founder of the company German Bionic Systems, which develops and produces exoskeletons for industry use case. With that background and all the experience ranging from research and all the way up to the deployment of industrial applications, we're very pleased to hear about your presentation. So, Dr. Heiligensetzer, thanks for coming today, joining today, and you can now start your presentation.
Yeah. First of all, thank you very much for inviting me to say a few words about our technology and also that I can show what we did in history. So I assume I start with sharing my screen, right?
Yes.
Good. Okay. So can you see it? Is it visible?
Yes, that's perfect.
Okay. So, yeah, I want to say today a few words about safe human-robot collaboration in the industrial sector by using a capacitive proximity sensors. In general, my presentation will be also practical oriented because unfortunately I'm a couple of years away from university and from pure research, so maybe it's also interesting to hear about the real industrial world and also the standardization and so on. So this will be also an important part of my speech. So what I want to give an overview about our company MRK Systems GmbH, a few words, then saying something about the state of the art of standardization. As I mentioned, maybe it's not pure research, but of course it's very important if we come from academia to the industrial world that we should or we have to fulfill standards. I will also give you an overview about technical solutions in the field of collaborative robots and technologies there. And then I want to go more into detail about our specialty, our capacitive sensor that we are using with the robots, in general, the function principle we are using, one picture about field simulation that we did. Then what is very important in the development was the safety and the advancements that we did with our latest developments. And then having a few words about use cases, especially one from the automotive industry, which we are pretty strong in, and want to conclude in a summary and an outlook. Yeah, so to start about our company. So we founded MRK Systems GmbH now, I think 17 years ago. then human-robot collaboration was a very new field, because robots are always working, or at that time were only working behind fences. And I would say still nowadays also 95% of the robots are working like this. But it's an interesting niche, I would say. So we are small companies. We have 17 employees. We made close to 2 million euro turnover last year. As we are located in Augsburg, and as my background is also with a big Chinese robot manufacturer, KUKA, we are a development and system partner of KUKA. And what our main products, our main field is that we don't develop new robots, but we develop technology packages, so add-ons to the robot, like a hand-guided robot or this tactile skin, that enables the robot to do more than normal robots. So we have some development capabilities in sensorics, safety-related developments concerning EN 61508, for example, in electronics and software. And where we earn our money in is building cells. It's very important, because a robot alone is never doing anything. It's only valuable if you add some grippers to it and make the programming and PLC programming and so on. So building the complete cell is important, and this is our business. Or we integrate just our technologies, or also we can do just programming for the robot, or we are also offering human-robot collaboration consulting. So you can see this some steps from being very complex, like a cell building, to giving just consulting work. Good. So to start, an overview about the standardization scene. So when normally you're thinking about collaborating robots, everybody thinks about a small, lightweight robot that is close to the people, and maybe is allowed to touch the people, but not too hard. But actually, this is not really the truth. So there are also other possibilities. For example, it is possible, like you see in the picture up right, that you're working together with big robots, and you guide them by a joystick or by a force torque sensor, for example, being a little bit like a manipulator, or being something in between a robot and a manipulator, but also you can there achieve higher payloads, what is very interesting. Also, on the other hand, what you see on the bottom right corner, you can also use active optoelectrical devices like laser scanners, light curtains, and so on. This is possible also since years, or since decades, but also a stable, interesting technology. So it's not only this power and force limiting, it's also other technologies could be used there. But yeah, this power and force limiting, maybe it's the most interesting issue, because you can be very close to the robot, and the robot is still an autonomous machine. With this hand guiding robots, the robot, you do not avoid the human. The human is always necessary, but with collaborating robot in power and force limiting, the robot is moving autonomously. Maybe also something from the real industrial world. There's the robot standard, the ISO 10218, and this ISO 10218 has two sections. One section defines the naked robot itself that you want to use. And in that part of the standard, it's defined that the collaborative robot should have safe brakes, it should have axis limitation, and reduce speed, and maybe a force limitation or pressure limitation. So every basic technologies the naked robot should provide. That's the one side. And the other side, what is, I would say, even more important, is a standard for the system integrators and defining the robot application. Because a robot cell is not safe by its own. Integrator or somebody who is knowledgeable has to parameterize the robot. So, for example, if the robot has the ability to reduce the speed, then somebody should parameterize the robot correctly and also make the testings and validations. And also, if it's the criterion of power and force or pressure limitations. Somebody has to do the measurements. They have to fulfill certain proceeding. They have to be recorded. So there's a lot of work to be done around the robot. You cannot just put the robot on the table and let it run. So you have to do quite a couple of parameterization work. And then what you do finally, at least in Europe, you put a CE mark on a type plate on the robot cell, and you give an EC declaration of conformity, where you declare that the machine is safe. So this is an important step. And actually, this is something what our core knowledge is in, that we can use the collaborative robots and make a safe robot cell out of it. Good. When we now see to the collaborative market, probably you know all these products, but it's important to have this as an overview. Probably the market leader in every cobot application is Universal Robot. It's very interesting. I can recall 8 or 10 years ago when Universal was not existing and came to the market. I could not imagine that a new robot company would have such a big success as Universal does. But yeah, Universal Robot, I would say it's the standard for collaborative robots at the moment. The technology, what is behind, they are measuring the current in the motors, and they use the current when they have a collision. The current goes up, and this is detected and will be used as a safety feature. Yes, we are close to KUKA. Of course, the KUKA LBR EVA is a very interesting machine. Also monitors torque in each axis, but not by checking or by using the motor current, but by individual or own safety-related torque sensors. So this is, I would say, a little bit more sophisticated technology, and it's more technical inside, also I would say, but the thing is that also the robot is much more expensive than a Universal Robot. And this makes it in the market a bit difficult for the KUKA robots to compete against the Universals. But also there are others. For example, FANUC, as #1 worldwide industrial robots, they have also collaborative robots. For example, the CR35. I think at the moment they have also the CR7 and CR10. So their technology is they use a force torque sensor in the base plate of the robot, and if the robot hits something, the forces are then transferred through the robot arm to the base plate and check there. And so the FANUC robot can decide if there's a collision or not. Also interesting technology, also with the robot of such a big payload, but yeah, in the real world, I didn't see so many applications because the robot is fairly slow, and this makes it difficult for real use cases. Yeah, finally, I want also to add a robot already working also with proximity sensors, with capacitive proximity sensors. So Bosch has a product there, the APAS system. So inside is a FANUC robot or a KUKA robot. Both versions are existing, and they have capacitive proximity sensors, approximately with a distance of 3 centimeters. An approach is detected, and then the robot stops immediately. It's a nice system. 3 centimeters is a bit short, but it's a different principle than the others. So that's a rough overview about the collaborating robots. Yeah, when we started in this technology, we also, of course, use Universal Robot and others, but I'm still very in favor of this proximity sensing, not to have a physical contact, but to stop before a contact occurs. So short video in general, how it looks like. So this is the robot, and it has sensors inside, and if somebody approaches the robot gives a reaction and stops. As mentioned before, in this standard ISO 10218, there are a couple of criterions that can be fulfilled to enable such a safe human-robot collaboration. And even though we have a proximity, we still argue in this power and force limit. But just be saying we don't want to have any force. So we stop 1 millimeter before the actual contact, same argumentation and same criterion of the standard, but with no force and also with no problems in measurements. Yes, so having some technical details about our measurement principle. So capacitive sensors are, it's a fairly old technology. So a background is it's a capacitor with in general 2 plates. The system that we are using uses 3 plates. So there's an excitation electrode. There's the ground, the surrounding ground, and they are creating an electrical field. And we have an additional measuring electrode where we get the measuring signal from. The field around that is creating, it's a straight field, it's in front of the sensor. And if an obstacle or if the environment changes around the sensor, this electrical field would change. And this can be detected by the voltage that is taken from the measuring electrode. So that's the core idea of the system. Yeah, as I mentioned, the electrical capacity is the input parameter for the sensor, and it's when you see the voltage, it's an AC voltage, but to use it an output signal, we rectify it. And if you put it on a characteristic, you see on the right side, you have a relationship between the distance to an object. We use an object that is close from the electrical behavior to a human hand, and the sensor voltage that is taken from this measuring electrode. And you see, the closer you come, here is 60 centimeters, 40 centimeters, 20, the closer you come to the electrode or to the sensor, the higher this measuring voltage goes up. And so we define just a threshold, and to this threshold we define that an approach is occurring. As it is a real world and there's also some ground close by, so the basic sensor voltage it's never zero, it comes to a certain value, and at the beginning of the measurement we just take this as a reference, and our calculated values are then just the difference there. What is also important when the field is created by the capacitive sensor, it's depending on the sensor geometry. And we used different shapes of sensor geometry because we mounted to the robot. And there are programs that can simulate the electrical field, and so also in relation to the distance where objects can be detected. So you can see here for the basic sensor geometry, the behavior of the electrical field, how the field lines behave if some object occurs. Here you see a finger. So a finger creates such a block to it. Or if you have a complete human hand, then it just gets smaller or already detected. And also we can do simulations where we mount the electrodes to the robot arm. So this helps us when we are developing electrodes on the right shape to the robot. So this basic technologies we are working since now a couple of years now. When coming to a product or using it for safety related issues, we put a lot of effort and optimize the EMC characteristics. So of course, by definition, a capacitive sensor creates a field has some EMC behavior, but also in a certain range. And there are standards that are defining in what frequency and what strength EMC signals allowed and what not. So in this band, we have to optimize our exciting electrode. Also, we are using microcontrollers. Actually, we're using 2 microcontrollers that are doing a cross calculation, and so checks each other if the calculations are still correct. And also, this creation of this excitation field is done by this microcontroller. What we also found out in our testings that the temperature is also a strong influence we have to take care of. So we do the whole circuit as temperature stable as possible, but we're also using an active compensation algorithm. So we have sensors on our board and also on the electrodes, and we have a certain algorithm that is compensating temperature-caused drifting effects. Also important to achieve a large detection distance. Finally, 2 more things which are also very important. It's the monitoring of the ground contact, as ground is one of our 3 electrodes, and we creating the electrical fields between the ground and the exciting electrode. It's important that this ground connection also have a certain quality. And if there's a problem with this ground connection, it might lead to a bad measuring behavior, what is not nice for normal sensors, but if we use the sensors in a safety-rated way, it's a no-go. So this is one example of failures we have to take care of, otherwise we could not use the sensor for safety-related tasks. And also, standard procedure in using safety technology is if you have signals, you don't use constant signals. You always want to have a dynamized signal so that you see that something is happening all the time, what you are expecting. So not that some sensor values are freezed and then you cannot have the guarantee that you can still use it for safety-related measurements. So dynamized signal is also very important, and all of these together in combination with documented development and risk analysis, we are in the process of certifying it with the IFA. It's a German certification institute. But it's a difficult way coming from a sensor principle to a really certified sensor. Here it's coming now to more again to the use cases or to the practical use. Most of the collaborating robots at the moment use the principle of having a contact and then stopping. Having a contact is always bad, because then you have the impact and you have some forces to the human body. Of course, these forces are not too high, but it's never nice if you are hit by a robot. Nobody likes it. And of course, the principle, if you have a measuring distance of 50 millimeters, the robot can have a certain speed and then get a stop signal and then has 50 millimeters to stop. So the robot cannot move very fast. So the larger the detection distance, the faster the robot can move. And robots always want to move fast, because fast moving is cycle time, is money. So in the real case, it's always good to run the robot as fast as possible. And if you have a larger detection range, that is extremely valuable for such robot applications. So here the theoretical calculation. So if what we achieve with 250 millimeters, we can be 2.2 times faster than a robot with just 50 millimeters. And that is really an argument for real use cases. So the real use cases, one example at Audi, it's probably you know, a German car manufacturer, a nice one.
Roboter prägen schon lange das Bild der modernen Automobilproduktion. Gerade die körperlich schweren und monotonen Arbeiten.
Can you hear the Can you hear the sound?
Yes, we can hear it.
Okay. So yeah, probably I just leave unfortunately it's in German, but it's a nice movie, so I think you get the impression.
Yes.
Die Zusammenarbeit zwischen Mensch und Roboter nun intensiviert. Seit wenigen Wochen wird am Bandabschnitt 3 der Montage A4, A5, Q5 die sogenannte Mensch-Roboter-Kooperation, kurz MRK, erprobt. Die Sicherheitszone wird nicht mehr benötigt. Roboter und Mensch arbeiten nun Hand in Hand und die Maschine wird immer mehr zu einem vollwertigen Kollegen.
Wir nutzen die kognitiven Fähigkeiten des Menschen, seine Feinfühligkeit und seine Anpassungsfähigkeit. Und wir nutzen den Roboter in den Dingen, in denen er gut ist, nämlich monotone Tätigkeiten auszuführen und eben Sachen für uns zu erledigen, die uns vielleicht Rückenschmerzen oder dergleichen bereiten.
Die Mitarbeiter werden im Schnitt immer älter, die Produktion immer komplexer. Deshalb soll der Mitarbeiter an der Linie entlastet werden.
So hat unsere Arbeit erleichtert, ist ergonomisch. Das muss ich sagen, ergonomisch ist präzise, entlastet unsere Rücken.
Die Zusammenarbeit von Roboter und Mitarbeiter ist eine absolute Neuerung im VW-Konzern. Der Roboter erkennt selbstständig, wann der Arbeitsschritt abgeschlossen ist. Beim Lösen des Füllschlauches bereitet der Roboterarm schon die Übergabe des nächsten Behälters vor. Der Mitarbeiter muss nur noch zugreifen. Zuvor muss der Roboter sich jedoch das Teil aus dem Container heraussuchen und ansaugen.
Die Teile liegen eigentlich wahllos in dem Ladungsträger drin. Und der Roboter muss sich selbst immer suchen, wo liegt das richtige Teil und wo kann ich es anpacken und muss dementsprechend die Bahn planen, um sich so ein Teil rauszugreifen.
Dabei hilft ihm die eingebaute 3D-Sensorik. Der Mitarbeiter spart sich dadurch das Beugen in den Behälter und schont seinen Rücken. Das Thema Sicherheit spielt beim Einsatz von Robotern in Menschennähe natürlich eine große Rolle. Auch hier waren die Entwickler erfinderisch.
Wenn ich in Kontakt mit dem Roboter komme, würde es mir nicht wehtun. Und zum Zweiten sind in dieser Schutzhaut taktile Schaltelemente enthalten. Die kann man sich vorstellen wie 1000 Notausschalter. Das heißt, sobald ich in diesen Schaum eintauche, schaltet der Roboter sofort sicher ab.
Ein sehr sensibler Kollege also. Die Mensch-Roboter-Kooperation wird eine Zukunft bei Audi haben, denn Audi plant weitere Einsatzmöglichkeiten, auch an internationalen Standorten.
Okay, so sorry, it was in German, but it was such a nice movie, and also with the speech of the Audi guys, if you could understand it, was very interesting. So other applications, here we see we also use it for palletizing application. There we also have in the tool area the sensor, also very nice, but this was not in a real application. This was in a demo application. So, but in general, robots that are stopping before hitting something is, I would say, always interesting. Good. Yeah, so coming slowly to an end of my presentation. So some summaries and some additional thoughts. So yeah, in general, as I mentioned before, so this human-robot collaboration with cobots, with power and force limitation and small robots is a very interesting way of acting together with a robot, but it's not the only one. So also speaking in real world, if you have the possibility to use a laser scanner, then probably you should use it because it's a stable technology. You don't have to do measurements with the collisions and so on, and it's very nice. But of course, this power and force limitation, as we have it with the other cobots, is very interesting because you can come close to the robot. When you saw the video of Audi, it's the same in every car factory everywhere in the world. In the final assembly, the space is limited, and there are always people running around, and you cannot do fences, and you also cannot realize big distances to the robots. So you have to be close to the robot, even with proximity, short-range sensors, or with this contact allowing robots. So very interesting. And also you see here on the right corner, this is a picture from Volkswagen in Zwickau, where they're producing the ID.3. So I think it's coming more and more in the automotive final assembly. Yeah, as mentioned before, this to having a proximity sensor instead of the real contact has some advantages, because this measurements are very difficult, and you have always to argue what special movement case you're measuring. So if you can guarantee that you don't have an really physical contact, that you're stopping 1 millimeter before, then it's much easier to realize applications. And then it's just a question what sensor principle you use. So there's also ultrasonic or radar sensors, and every had maybe advantages and disadvantages. Our choice was the capacitive sensor, because the physical background that you are detecting objects that are disturbing the electrical field, like water, like the human is out of water, is very good. And also when you have a sensor, then there's a sphere around the sensor, and there's some general advantages of the sensor principle. But what you have to achieve is you have to do it in a safety-related way, and there are many standards, for example, for sensors or for safety-related parts of control systems. There's the EN ISO 13849, and the sensor has to be has to fulfill this specifications there. Also, as mentioned, even if the robot is safe, the whole application is not yet safe, because the safest robot with nice proximity sensors, which have a knife in its hand, could not be safe. So entire robot set is important, risk analysis. So probably you have to do also something with the tool protection system. So there's still a high requirement to system integrators or to the internal company knowledge for safety, because even a robot that can handle 10 kilo, what you would achieve is not much, can do really big harm to the human if it's not programmed well. Good. So some additional thoughts. So human-robot collaboration is not always the best choice. So also, even if it's my personal thing, if I see I could do an application without human-robot collaboration, just using fences, I would do so, because normally it's always easier and always cheaper, but there is a niche, and it makes sense when there's not much space, like automotive final assembly, or if you have to refit old applications where already humans are involved, then it makes perfectly sense. The challenges in this human-robot collaboration is always the gripping in the contact situation, because when you have the hand in between and the robot is coming, then this is always a problem. And also the economics, because standard robots are fairly cheap, and if you have to do a lot of engineering and a lot of thoughts about safety, the cost for such an application goes up, and then might make no sense to use the robot anymore. For the capacitive system, what is very nice, so the future could be that we also take into account the environment, because at the moment, if you have a dumb sensor, it cannot decide if there's a human standing, or if there's just a car standing, or something from the environment. But if you can learn the environment by teaching maybe a reference part, or you do a workspace exploration, then the sensor or the robot system can decide if it's human or if it belongs just to the environment, and then makes it easier also for the tool area to have a protection. Also, what is nice with the capacitive sensor, it's not only limited by small robots. For example, when thinking about the Fennock CR35, because it's so big and so heavy, it has a certain stopping distance, it has to move so slow. But if such a robot can be equipped with proximity sensors, the speed might be higher. It might not be extremely high, but higher and reasonable for real applications. And so also this human-robot collaboration can be used for robots in a higher payload range. Good. So far to my presentation. I hope you got something from it, and yeah, I'm ready for feedback or questions.
Right. Thank you very much. Thank you for a nice presentation, and also for giving us the insights on the development of the sensors and the certification process. So usually as a researcher, you usually just don't deal with safety certification or specifications, but at least not that intensively, and that's a nice perspective for us. Does anybody have questions? Yes, Stefan?
I have a question. Yeah, thank you, Peter, for your presentation. It's very interesting. I wonder about what I want to say, the value proposition of this type of technology, and I'm curious also in making the difference between fenceless automation, so meaning automation that's happening with robot sharing a common space with the human, but not necessarily interacting to solve a task, versus human-robot collaboration, where the task is solved by the robot and the human interacting. And so I thought that is fenceless automation maybe a more attractive value proposition than the actual collaboration between human and the robot? Is there something that's happening in that domain?
Yeah, so real collaboration where the human and the robot are at the same part and doing something at the same time, it's very seldom. It's really not very often. It's really more the coexistence that about sharing the same workspace, but not working together. And if you have enough space, then you would just do a fence around the robot. It's only the case when the human is very close to the robot and you cannot do fences, then you have this coexistence case. But I think this is much more interesting than having real collaboration.
All right, so it's really about the place, the real estate on the shop floor, right? So that you have the available space for the humans and robots to be in. So if we improve this technology, or if we improve the certification procedure and so on, it means that we can automate in spaces that we previously couldn't, and therefore we have an interesting value proposition.
Exactly.
Yeah, okay. Thank you.
Welcome.
Any further questions?
Maybe I can just add a question.
Yes, sure.
Maybe it's a bit provocative, but let's see. First of all, yeah, thanks for the very nice presentation. I want to see what your view is on soft robots, and one might argue if you use soft robots, soft material robots in these environments, maybe you don't need all these sensing technology that can measure how close someone is to the robot, because they are, soft and inherently safe.
What exactly would you define as soft robots that you can push away, or?
When there are different people and different views on what a soft robot is. So for me, a soft robot is a robot made from soft materials. So for example, from silicone, rubber, or fabric even.
Mm-hmm. So I would say if you can really create such a robot out of soft materials, then it would be safe. But the question is, can it really do some work? Can it really handle weight in a certain speed? Because that's all about. So an industrial robot handles a lot of weight in a large speed. And the quicker and the more payload it has, the more productive actually it is. But of course, if the human is then close and he gets hit by the robot or even clamped somewhere, then it's extremely dangerous. And so this has to be avoided somehow. So I can recall there was a company called BioRob a couple of years ago. It was very lightweight robot arm, only 300 grams of payload, but it was inherently safe because it was so soft everywhere, but you could not use it for the task. And that's the problem. And at least I don't know, because I'm very industrial oriented, and there's only the question cycle time, speed, and payload, and for robots less than 2 kilograms, I don't see the real use case.
Okay, yeah, no, thanks. Payload is definitely an issue. Yeah, thank you very much.
Right. Further questions? If not,
I have
okay.
one, yeah. Hi, thanks for the presentation. I have a question regarding the decision of using capacitive sensors. I'm also doing some work with capacitive sensors and with radars, and one of the things we always say, so usually people ask, why is all of this not done with a camera? And there are many reasons. So we always say, even for indoor applications, you might have the problems of bad lighting, dust, staining, etc. But there is also another argument that frequently comes up, and I wanted to ask for your opinion and experience in this, which is the fact that people may not be very comfortable with the idea of being recorded by a camera while working. Is this something that ever happened also to you or in your experience?
I could imagine this. We never had a discussion about this and really asked people, would you like to have a camera or not? But I could really think that it would be the case, that people don't like to be monitored all the time, even if you're telling them it's only for protection reasons and data are not scored and so on. But people don't like it. So that's also our thing. And the real decision if a radar sensor is better than a capacitive sensor or ultrasonic, I think the technology has to show it what is really the best solution there. So I heard also about, we did not do tests ourselves, just read something about radar sensors. They're also very nice and useful. Yeah, we decided 10 years ago or so, and yeah. But with the camera, you are right. I think people would not like to be monitored all the time.
Yeah, yeah. Okay, thank you.
Yeah, you're welcome.
Right. Then maybe I will add one or two questions. I saw your video with the robotics skin in an industrial application. So did you have this or go through the certification process or how did you achieve these specifications that are or the ISO specifications? Because usually, as everyone knows, with capacitive sensors, it's hard to infer distance information from capacitive readings because the readings depend on so many parameters like the shape of the objects or materials. So in your case, you're saying that you're allowing zero forces in regards to power and force limiting. And do you have some kind of reference object or a model of a human or human limb which you use to calibrate your sensors?
Yeah. So I understood two questions. So first question about where we are in the certification process. So it's a stony way, and we are not yet really through the certification process with our capacitive sensor. And what you saw, the nice video of Audi, of course, Audi would not use a system that is not 110% safe. So at Audi, it's a combination. So we use the capacitive system, you can say, as an add-on, and we also have a foam padding around and tactile switches like a safety net put in. So it's a very the old-fashioned technology, but it's 100% safe technology, and we have the capacitive as an add-on, and we can see it in the behavior in the real world. So that was the trick there. And in some details in our certification process, so we define the smallest part of the human and what is a finger. And so we created a reference object with the electrical behavior of a finger, because we cannot use, one has a longer finger and another a shorter finger. So we defined together with the certification institution a reference finger, and this we are using. So probably we achieved 25 centimeters with a finger, but we cannot decide. So we would, if somebody approaches with the full body, it might be detected in 40 centimeters, but never less than 25 centimeters. So this is the argumentation.
Okay. So the idea is to perform more conservative,
yes,
on a more conservative way.
Yeah, more conservative, yeah. Also with this temperature thing, we can compensate it and good, but overall we have to be more conservative. So in the best case, we would detect a bit more.
Okay, but that leads me maybe to another question, maybe the last question. So do you think that with pure capacitive sensing, will this technology outperform like force or impedance control systems, because actually what capacitive sensing does is it reacts more conservative, or maybe that much conservative that maybe contact-based sensing like impedance or force control may outperform it with regards to speed, for example.
The nice thing with this proximity detection is that you can argue you don't have a contact. You don't have to measure things, but if you have impedance control, also force control, you first have a certain contact. And if you have even a very slow contact, then you have to do measurements, you have to do documentation about it, you have to redo it every year and so on. There's a lot of work. And of course, with the proximity, you also maybe have to do something, but you can just show, we're stopping before. And that makes it much easier. And that's the core reason.
Right.
Sorry, I just want to ask something that comes from here.
Let me just, sorry, excuse me to interrupt shortly, because I think we're kind of late in the time.
We're out of time. Okay, we will talk about it.
Actually, I wanted to ask if, Rebecca, if you have to leave at some point.
Sorry.
Yeah, because
I don't have to leave until 10 my time, so a little over an hour. So I think we should be okay on time. Thank you, though.
Okay, great, thanks.
But I think Lisa wants to introduce Rebecca, and she has only time until 3 o'clock. So maybe we can switch further discussions to maybe after the session, and maybe if it's okay for you, Francesca, that we first let Rebecca have her talk.
Yes, absolutely.
All right.
Okay, so thank you very much for your attention. So I switched off, and unfortunately, I also have to leave at 3. But you are invited anytime to call me directly if you have any questions.
All right. Yes.
Okay.
Thank you very much.
Thank you, Peter.
I'm quite.
All right. Then we have next Rebecca, and Lisa will introduce her.
Thank you very much for your flexibility. That's of great help for me. Yes, so it is my honor to introduce Rebecca Kramer-Botigglio today. She's an associate professor of mechanical engineering and material science at Yale University. And her work focuses especially on the intersection of materials manufacturing and robotics and its soft systems. As we have learned already today, she's deriving new functional materials for next generation robots so that they can adapt their morphology and of course also their behavior to changing tasks and environments. And Rebecca has received numerous early career awards. She was named to Forbes 30 under 30 list for her approach to manufacture liquid metals through printable dispersions. And that's also where I know her research from, stretchable sensors based on liquid metals. And she especially also serves in various academic roles, such as associate editor for soft robotics, multifunctional materials, and transactions on robotics. We are very happy to have her here today, and she will give us a talk titled Integrated Sensing in Soft Robots with Adaptive Morphology. So the stage is yours, Rebecca.
Thank you so much for the introduction, and thank you also for inviting me to participate in your workshop. So let me go ahead and share my screen. All right, is everyone seeing my screen? I see nodding. Great.
Yes.
Okay. Yeah, thanks again for the introduction. Thank you for inviting me. As mentioned, I'm going to talk about integrated sensing in soft robots with adaptive morphology. So you can see one of the robots I'm going to talk about on the title screen, our recent work on robotic fabrics. And I'm also excited to present some unpublished work as well. So this is actually, I think, pretty interesting following the last talk, Peter's talk, where he talked about automotive robots. So usually what I say here is that, these are standard the typical rigid robots, here on an automotive manufacturing line. And these robots are extremely good at what they're designed to do. They're very fast and strong and precise. But what they are typically not is safe for human robot interaction. Although I think our last talk may have convinced me slightly otherwise, that more recent robots in this, towards these manufacturing lines are becoming safer for human robot interaction. But what they are still not is adaptive. So you don't see these robots adapting to changing tasks and environments, and they don't need to in this case. They're not changing their environment, they're not changing their task. But when we think of robots for the future, I think we all imagine something more like this, like animals like ourselves. We are incredibly adaptive. We behave in many different environments. We readily adapt our morphology and our behavior toward these changing tasks and environments. So how do animals do this, and how do we get robots to do this? Well, I noticed something while watching all of these videos. All of these animals look at least partially soft. So we can take a deeper dive into that observation. So here's a plot of all the known animals in the world, just over 1 million at the time of this data. And as it turns out, all known animals in the world are at least partially soft. There are no known animals that are completely rigid, which is in contrast to the way that we typically design machines and design robots. And if you look even closer, over half of all animals known are completely soft. So there are some caveats here. Completely soft animals need to be supported by their environment. So you think of jellyfish that live in the water or worms that live in the ground. We as humans are a fairly large animal, and we require our skeletal structure to keep us standing up on the ground. But even we are only 15% bone and 85% soft and fluid materials. So maybe there's something here. Is it possible that our soft material composition actually plays a role in our ability to interact with and adapt to our environment? So this is a question that I am thinking about, and that many people are thinking about. Soft robotics in general, this approach of using soft materials in robots, it is becoming really, really common in the academic community. So there's many, many soft roboticists. It's a rapidly growing field, and there's many benefits to soft robots. So here's just a few soft robots that I think showcase these benefits very well. So in this first video, you saw this locomoting soft robot walking out into the street, gets run over by a car, and it's able to continue locomotion despite the impact of the car. In this middle image here, you can see a soft robotic gripper designed by Soft Robotics Inc. And it's able to conform around diverse and delicate objects due to that soft material conforming around the objects it's gripping. And over here, you can see a wearable soft robot. And again, that the soft materials kind of conforming to the body allow it to the robot to assist the wearer or augment load capacity without restricting the natural mechanics of motion. But all of these robots, and most robots, are very task specific. So they're designed to perform a very specific task, and they don't lend well to tasks outside of that designed use case. So locomoting robots often don't perform well as wearables or as grippers, and so on. And so this is the question that I'm really interested in. Can we design more adaptive robots? So this is kind of the central focus of my group right now. We're working at the interface of materials and manufacturing and robotics, and trying to use new materials and incorporate them into robot constructs in order to achieve this new function of adaptive morphology and behavioral control policy. So we have a few different adaptive robot platforms, robotic skins, robotic fabrics, a robot with morphing limbs for amphibious locomotion in 2 different environments. I won't talk about all of them today due to time limitations. I will mention, I'm not going to talk about our robotic skins, but you can see that we, just because this is following Peter's talk for the last talk, and he talked a lot about capacitive sensors. So we've also incorporated capacitive sensors for all of the reasons and benefits that he described in his talk. So I think it's fitting that I omitted that from my talk today, but I'm going to focus on robotic fabrics and morphing limbs. So diving right in, we'll get into robotic fabrics. Okay, what is a robotic fabric? I think definitions are always variable between people. Here, we describe a robotic fabric as simply a fabric that has been roboticized. So fabrics are incredibly ubiquitous. I'm wearing fabrics. My chair I'm sitting on is fabric. My backpack is fabric. You are also probably wearing fabrics. They're just all around us. And the idea of actually roboticizing or implementing some functionality into these inert, typically inert passive materials is really appealing. So what we did is we created a suite of functional fibers to achieve actuation, sensing, and variable stiffness, and incorporated those into fabrics. So I'll get into this kind of suite of 3 different functional fibers in a bit more detail, and I will focus on the sensing, given that this is a workshop on proximity sensing. So starting with the actuation, we use shape memory alloy and nitinol shape memory alloy, and typically this is made in just round form, but we found that when we integrated antagonistic wire bending actuators into fabric, that off-center forces can encourage the wire to twist rather than bend in its couching. Couching is what we use to attach it to the fabric, and this can cause some kind of chaotic actuation. And so we were able to overcome this challenge by flattening the wire. So we flatten it out into these SMA nitinol ribbons as opposed to wires. And that allows us to get this really clean actuating, this bending actuation of the fabric. Okay, and then moving over to variable stiffness, we developed these variable stiffness fibers. They're made from a composite of epoxy, which has a glass transition temperature, a thermoset epoxy, and then incorporated Field's metal particles. So Field's metal is an alloy of indium, bismuth, and tin, has a melting temperature around 62 degrees Celsius. And this gives us this 2-tiered softening effect. So when the material is cool, the epoxy is pretty rigid, and it has these solid metal particles in it. So the whole thing takes on a very rigid composition. And when we apply some heat, when we heat it up, the epoxy undergoes its glass transition temperature. So it softens by about an order of magnitude, but then also the included metal particles, they melt. So now instead of having these rigid metal particles suspended, we have liquid particles suspended, and it undergoes an increased softening effect. And so we see this almost 3 order of magnitude change in stiffness between the cool state and the hot state. And then we're able to form these into these nice fibers that you see and incorporate them again into standard fabrics to apply variable stiffness. Which I think is an important point given, the last talk we were talking about, the need for soft robots to also be able to do work and bear loads, payloads. And I think that variable stiffness materials can start to get at this problem that we see with soft robots. And then finally, I will focus on the sensing element in our robotic fabrics. So we developed this Pickering emulsion in order to incorporate sensing directly into textiles. So this was a really clever idea put forward by one of my former postdocs, Dr. Sang-Yup Kim. And his idea was to essentially take conductive composites and suspend them as an emulsion in a non-viscous carrier solvent. So what we have here in the schematic is a pre-cure silicone particle. So this is PDMS, and it's uncured, and it's stabilized by these small carbon black nanoparticles on the surface. And then these are all suspended in ethanol, a very non-viscous, gentle solvent. And then when we deposit these on a surface, on a textile or non-textile surface, the ethanol evaporates away, and it allows these particles to start coalescing and self-assembling on the surface to create a conductive composite that can perform as either a resistive strain sensor or an electrode to a capacitive strain sensor. So we can start to do some interesting things with these, looking at printing them onto substrates. So here you can see, again, we have these conductive composite particles suspended in ethanol. It's very gentle. We're putting it onto a balloon here, just kind of pasting it on. I'll pause this for a second just to kind of focus on, the stability and the printability of the ink. And we contrast that with a typical conductive composite, which usually needs to be thinned. So you would have a conductive composite, need to thin it out in order to print it. You thin it out with usually a toxic solvent like cyclohexane or toluene. And then as you can see, when you put that onto a substrate, it will cause damage. So that can be challenging for wearability, putting it onto fabrics or any kind of elastomer or latex substrate. Okay, so now that we can paint these things onto things like balloons, we had the idea to make a self-sensing McKibben actuator. So here we have our Pickering emulsion painted onto a latex balloon, and it's inside a mesh to create a standard McKibben actuator, and we get this self-sensing controlled behavior. So here we're just using the sensor painted onto the balloon to track the set points. The black line here is the set point, and the red line is the actual controlled length of the sensor. Okay, and of a special interest to robotic fabrics, as it turns out, we weren't quite expecting this, but when we print this onto a fabric substrate, the conductive composite self-assembles around the individual fibers as opposed to filling the gaps between them, which is what we would typically see with a more viscous or thin conductive composite. So we print this onto, standard fabrics like cotton or muslin or nylon, and we can see, this is the neat fabric backlit. We have about 5% porosity. When we print our Pickering emulsion sensor onto it, we retain a lot of that porosity, about almost 3% porosity. And you can see in the strained case that we increase that porosity further. So this is really important for retaining the properties of the fabric. So if we want to use these, especially for wearables, we want to retain that porosity and breathability for comfort. So here we painted the Pickering emulsion sensor onto kinesthesiology tape. So this is a standard fabric tape that's used to usually support athletes without restricting their motions. And you can see that the raw sensor data coming out of the sensor. And here the sensors are placed into a fully robotic fabric. So we have our Shape Memory alloy ribbons incorporated into the fabric, and the fabric is being commanded to simply bend up and bend down. And then we have sensors, the Pickering emulsion sensors, that are printed onto the top side of the fabric and the bottom side of the fabric, and they're being used to actually control that upward and downward motion. Although you can see it's a little bit jumpy. So here are some full robotic fabric demonstrations, showing the shape-changing behavior and potentials for robotic fabrics. So in this case, the fabric starts out in this flat configuration. It softens its variable stiffness frame and then uses its actuators to stand up into kind of a table-like structure. And then we place weights on top of the structure. And in a moment, you'll see that we soften it again and the whole thing settles back down into its initial flat configuration. So I think this demonstration shows how we could potentially use these for self-deploying structures, things like deploying tents, and load-bearing systems. And we're working on the system now to make it actually dynamic into a dynamic walker that can carry loads. So here's another demonstration of the robotic fabrics in action. So we had these wings that are rigid initially. We soften the variable stiffness fibers. The wings curl around the fuselage in order to take up very low volume during storage and transport, and then can self-deploy and become rigid and load-bearing again in order to actually perform as a flyer. So we don't actually show this flying. However, the system is fully untethered. So I will note that all of the electronics, controllers, batteries are inside this fuselage. And it's a fully untethered demonstration. Okay, and finally, to showcase potential wearability of robotic fabrics and also the utility of the sensors a bit more, we have this reactive robotic tourniquet demonstration. So here, this would emulate the idea of damage. So upon injury, the sensor might be cut. The broken sensor triggers a reaction. So the variable stiffness fibers soften again. The actuators compress in order to apply, really constrained blood flow through the limb here that's being simulated by this foam. And then the variable stiffness fibers become rigid again in order to hold that compressed position without any additional power supply. Okay, so I'm going to switch topics now away from robotic fabrics and the Pickering emulsion-based, printable sensors, and I'm going to talk about one more kind of adaptive platform that we're working on, which is a morphing limb platform for amphibious locomotion. Okay, so the basic idea here is that we took inspiration from two very morphologically similar animals, sea turtles and land tortoises, which have, their morphology, this common hull in common, but they differ primarily in their limbs. So land tortoises have a rounded limb that's better for load bearing, and sea turtles have this very flattened flipper that's better for hydrodynamic efficiency in the water. So we developed this soft robotic morphing limb. It uses very similar materials and technology to the robotic fabrics we just saw. So this has fluidic actuators that are coupled to a thermoset epoxy. And so it starts initially in this neutral flipper configuration. You can see copper laser cut heaters here. We apply heat, it softens the epoxy, makes the whole thing very soft. We can use our fluidic actuators to morph the limb into this rounded load-bearing configuration, and you can see that the bottom of the limb actually curls forward to create a foot. So this is the foot of the limb. And then we just cool the whole system in order to lock the new shape in place. And this allows us to transition between something that looks more like a flipper and more like a leg for swimming in the water and walking on land. Okay, so we can actually see the robot doing these things, swimming in water first. So to be clear, this is not our actual robot. This is a sea turtle. But here to show the similarities between our robot's behavior and the real sea turtle. And these three videos do showcase our real robot doing some different maneuvers, such as submerged lift and diving, and some surface swimming as well, using different gaits. Okay, so now if we flip over to leg mode, we can see how the robot behaves on land. This is a more challenging environment, a little less stable since we don't have that support from the water anymore. Here you see our animal inspiration, the land tortoise walking towards us, and our robot using a similar creeping gait. Very stable gait means that three legs are always in contact with the ground. And it's on different substrates here. So here it's walking on our lab tiled floor, and here it's walking on a more representative transition substrate of water and sand and pebbles. Okay, and then we explored one further gait for this robot. So again, looking at our inspiration animal, here we have sea turtles that are crawling up the beach. So this is looking at kind of the amphibious behaviors of sea turtles. And showing how our robot can take inspiration from, how they transition from the water to the land. So they use something that we like to call a beach crawl to crawl up the beach. And we, implemented a similar gait in our robot to show crawling on sand. And again, our more transition substrate of sand and pebbles and water. Okay, so we don't actually have any sensors in this robot. And given that this is a workshop on proximity sensing, I wanted to showcase this system and kind of speculate on proximity sensing and what that would mean for the robot, and how we could, in the future, embed a suite of sensors in this robot to automate these behaviors. So right now we have developed this platform. We've primarily focused on the development of this morphing limb and achieving this, different behaviors, the swimming behavior in water and hydrodynamic efficiency, and lowering the cost of transport during terrestrial gaits on land. But the transition is a very interesting zone to study, and looking at the amphibious behaviors of animals going across that transition is really enlightening, and it's been a lot of fun for our project. So as we kind of further develop the system and think about the transition between water and land and water, and different environments in general, we think about, what kind of sensors would enable us to automate and really optimize this transitional behavior. So we think about distributed strain sensors for limb state, and there are many options. There's the capacitive sensors that we've developed in the past. There's our Pickering emulsion sensors that I talked about today, which enable printability onto any kind of substrate and really allow for free form and distributed integration of sensors into the limb potentially. And then there's our liquid metal sensors. that we've developed in the past as well that I also didn't discuss today. We could also embed pressure sensors, in the foot, in the contact between the limb and the ground, in order to estimate ground stiffness. Sorry, that's a typo. It says group. It should say ground stiffness, incline and friction with the ground. We've thought about incorporating IMUs in the body to sense orientation, especially for thinking about wave energy and how the robot might be tousled around in the water a bit, and then adding cameras for teleoperation as well. So I hope this can spur some discussion about how sensing in general and proximity sensing might enable further development of this robot. So I will end there. I want to thank my group and also thank you for your attention.
Yes, thank you. All right. First question from Kaspar.
Yeah, hi Rebecca. Very nice presentation. Really, I like in particular the turtle robot, or should I say, is it a tortoise robot? It's always very confusing.
Turtle and tortoise inspired. Yeah, both.
Both. That's the answer, exactly. Anyway, I just wanted to see whether you could comment on the speed of your sensors and your actuators, and I'm asking in particular because some of the actuators use shape memory alloys, and they are known to be a bit slow because you need to heat things up and then cool it down again. So how do your sensors perform in regards to time, speed?
Yeah, that's a great question. So are you specifically asking about the Pickering emulsion resistive sensors, or just sensors in general?
The sensors you are using. I mean, maybe they are fine for the slightly slower moving systems, or whenever you have for example, the folding plane-like structure, there, I suppose it takes some time for the folding to take place and the sensing might be adequate. But maybe your sensors can be also used at higher speeds.
Yeah, that's a really great question. And it's not something we've thoroughly quantified, so I might not give the most satisfying answer. I will say that I think the sensors benefit from the slow speeds of actuation. As you know, SMAs are not known to be incredibly fast actuators. We did look rigorously at the effects, the thermal effects on the sensors, just because we have two thermally responsive fibers in the robotic fabrics. We have the SMAs and the variable stiffness fibers that are also thermally responsive. So we did find that the sensors are not very affected by temperature. We found that, just removing them, having them placed away from a thermally responsive fiber by at least 3 millimeters, that's a very quantified number, would remove any effect from temperature. But we didn't look so much at time response. And I will note that, they are the Pickering emulsion sensors, once they're very advantageous for the printability, the fact that they can be made into these emulsions that are suspended in a very gentle, low viscosity carrier solvent. And so that enables us to print it into anything the way you would print ethanol. So you can basically adopt the printability of the carrier solvent. And that's the real benefit to the Pickering emulsion. Once they are deposited and the ethanol evaporates away and all the particles self-assemble and form into this conductive composite, it behaves like any other conductive composite. At the end of the day, it's silicone and carbon black. So it has all of the drawbacks of resistive sensors that we've seen. There is hysteresis, there is drift. So that the sensors, once they're formed, they behave the same as any other conductive composite, and they might perform better as electrodes in a capacitive sensor.
Okay, so okay, thanks for that. Maybe just out of curiosity, I liked your folding plane, but you said you didn't. It wasn't flying. So why? I mean, what held you back to make a flying system?
Yeah, flying is very difficult. There are researchers who specialize in this, and I am envious of their expertise. So we didn't we didn't put a lot of effort into making it a functional flyer. I will say that. We built this so that the project was initially funded by the U.S. Air Force, AFOSR, and so we wanted to create this morphing wing demonstration and really showcase how the wings could be stowed during transport and then deployed. But we didn't put a lot of effort into making it a functional flyer, and I suspect that that's an incredibly challenging effort to take on.
But fundamentally, I mean, as long as you have the right shape for your wing, should be possible. For someone
Yeah,
else,
I think the weight distribution in our current demonstration is not ideal.
Maybe an underwater glider could be the next step.
Yeah, I think that's a great suggestion.
Thank you very much. Thanks a lot.
Right. Next we have Stefan.
Yeah, thank you, Rebecca, for this very interesting talk. And I have a follow-up question to Kaspar's. So since you were thinking about planes, so you were also, I guess, maybe confident that you can scale this up. Is that something that you think is plausible?
I do think so. And in our paper that we published on this, we looked at scalability. So we thought a lot about how the fibers would scale, especially with respect to brittleness of the variable stiffness fibers, especially as you increase the aspect ratio, as they get longer and longer, we do have to be concerned about, they're essentially beams. But we do believe, we put in some, we kind of studied the scaling, and we put forward some guidelines as far as what we think the dimensions of fibers should be relative to the loads and length of that the beams are supporting. And so as long as it's designed that way, then yes, I think they do scale up. Did that answer your question? Maybe that's a long-winded answer.
No, yes, for sure. Yeah, honestly, I don't know a lot about the subject, but realizing that it was a small plane being demonstrated, and then the project being financed by the Air Force, I was imagining they had to find some interest in it, so they had to be larger planes.
Yeah.
Yeah, but yeah, thank you.
I have a last question. So I'm not a material scientist, so maybe this is a good point to ask about your what was called the sensor, or the sensor material you have developed. So as far as I understand from the slides, it's an emulsion of conductive particles in kind of ethanol or alcohol, and when you apply it on textile, it gets soaked up into the fabric, right?
It can, yeah. Depending on the textile, it can, but ethanol in particular evaporates very quickly.
Okay.
So we don't see a lot of absorption of the carrier solvent into the textile. It just evaporates away.
Okay. And after it evaporates, is it kind of, as far as I imagine, like a remaining residue of the conductive particles, but my imagination is like, well, I imagine that if the carrier is gone, will it still remain on the textile, or will it just dust off? Like if you have some kind of mud on your pants, or on some kind of fabric, if it dries, then it will just dust off.
Yeah, that's a great question. So especially on a textile, the fibers, if you look at the morphology of most textiles, it's rough. Even the individual fiber morphology can be kind of rough, because most fibers are actually agglomerates of fibers that are twisted together, and you can see a lot of kind of small offshoots creating this texture. And that texture works to our advantage. So the Pickering emulsion, this is it's a definition of a type of emulsion where you have a main fluid particle that's basically stabilized in the emulsion by smaller particles on the surface. So that's what we have. We have PDMS particles that are stabilized by these smaller carbon black nanoparticles all over its surface. So once the carrier ethanol evaporates away, all of these particles, they become unstable. They're no longer stabilized being in the emulsion. So they'll start to kind of fall apart, and we get this pre-cure PDMS, and all the carbon black particles, self-assemble within there, and they all just, coagulate and coalesce into a conductive composite, the way it would be if you just mixed carbon black into PDMS and put it down on the substrate. But we do get the nice kind of self-assembly around the individual fibers just because of the mechanism of printing it, and the ability for that carrier solvent takes a little bit of time to evaporate away. So it gives it that time to kind of seep around the fibers as opposed to filling the gaps between them. But I love your connection to mud, because if we print it onto especially more smooth substrate, so not textiles, if we just print it onto a very smooth substrate with not a lot of texture, we do see something kind of similar to the way mud dries. We see this cracking, like mud cracks, when the entire thing dries on the surface. And that's actually what enables the sensing mechanisms. That those cracks almost act like kirigami when we're pulling on the substrate. And that gives us a little bit of additional resistance change with strain, and enables the sensing mechanism. So it was a great observation on your part.
Yeah. So it's there's next to the carrier, there's some kind of silicone or PDMS, and then the conductive particles, and when the carrier evaporates, it solidifies. Or okay.
Yeah, I think you understand it perfectly.
All right. Yeah, that was my question, I think. Are there any further questions?
So I'll just note before we move on, I apologize. I'm in my office and there were some people knocking on my office door during my talk. So if I look, I hope it didn't seem like I was too distracted. I tried to block it out, but my apologies if I seemed a little distracted a couple of times.
Yeah, maybe I can cut it off.
Okay,
Right.
I tried to minimize it.
All right, then we can switch to the next speaker. I think it's Francesca, and Kaspar will introduce her.
Yeah, it gives me a great pleasure to introduce Francesca. She's doing her PhD in our robotics group at Queen Mary. Previously, Francesca was a research assistant at the University of Applied Sciences and Arts of Western Switzerland. But now, she's at Queen Mary and she's in the final year of her PhD and is contributing to the research that we are doing in the framework of the National Center for Nuclear Robotics. That is where Queen Mary is involved with. And here we are interested in finding robotic solutions for nuclear waste decommissioning. And her research in particular focuses on tactile sensing systems applied to extreme environments. And in particular, identifying surface properties using tactile and proximity sensors. But I just wanted to add that her interests really go beyond what is happening currently at Queen Mary, and because she is at the same time also a research assistant at Imperial College London, and there she's working in the UK Dementia Research Institute, which is part of the brain science department there. That is maybe something for another talk. Today she is focusing on crack detection and classification in extreme environments. And I pass over to her. The floor is yours, Francesca.
Thank you so much, Kaspar, for the great introduction. So let me share my screen. Okay. Can you see?
Yep, you're good.
So, okay. Oh, sorry. So hello everyone, my name is Francesca Palermo and I'm a PhD student at Queen Mary University of London, and I will present today my work on crack characterization via graph theory for exploration with a robotic manipulator. And this research has been developed in collaboration with the National Center for Nuclear Robotics. So one of the most important tasks in extreme environment is the detection of fracture and crack on objects used, for example, for keeping chemical radioactive waste. This crack may be caused by different reasons, so material degradation over time or environmental changes. The problem is that if these cracks are not detected in time, then they may lead to larger macro-scale catastrophic failures. Currently, in the state of the art, there are multiple methods for detecting cracks, mainly based on computer vision, which the problem is that is not applicable in extreme environments because the electronic components get degraded by the gamma radiation. And acousto-electric sensor, which actually requires to be embedded when building the structure. So on the other hand, tactile and proximity sensing can provide information on material properties that maybe computer vision may not be able to do. So for example, texture and the hardness, the stiffness of the explored object. So in my research, I'm using a tactile fiber optic based proximity sensor developed at Kramer University of London by Elisabetta Costantinova. This sensor is finger-shaped and it consists of 4 pairs of fiber optics, 3 positioned in the middle, 3 used for calculating the deformation of the middle soft part of the sensor, and then a pair positioned at the tip of the finger used to calculate the proximity of the explored surface. Let's say that the pro of using tactile proximity sensing and in this case fiber optic is that it doesn't have any onboard electronics, and in addition is robust to the gamma radiation which are found in extreme and nuclear environments. In the past, I developed a classifier based on force proximity data for the classification and let's say the analysis of explored surfaces. So this classifier was able to recognize if there was indeed a crack in the explored surface and which was the width of the crack of the surface using a random forest classifier and time domain features such as mean absolute value and root mean square. The problem with this kind of tactile only based approach is that it's really time consuming. So imagine that for exploring only a small surface of like 10 centimeters times 20 centimeters, it was requiring around 10 minutes, 15 minutes. So if you think about applying this kind of model, this kind of approach in an unconstrained and real unsupervised environment, then it will take really a lot of time and it may produce many errors. So the idea is to implement a multimodal approach. So using object detection extracted, so the video and images extracted by a camera, we can apply object detection and faster CNN on top of it. And then once the camera, let's say, will scan a surface, it can recognize and skim down the possible interesting location and send its coordinates to a robotic manipulator, which will have the sensor that I previously described attached as an effector. So the manipulator, once it receives the coordinates, can reposition itself and starts the exploration. And at the same time, an online classifier can indeed confirm if there is a crack or if it is just a false positive from vision. The experiments that I performed to validate this setup, I used haptic-based desktop interface called Gmagic, since I couldn't introduce a Franca Panda manipulator in my living room. And so the idea was to have these, because the experiments were done during lockdown, so it was almost impossible to bring the whole setup here at home. So the idea was to use this manipulator with attached an effector, as an effector, the sensor that I previously described, and then having a camera position on the top, which was scanning the area in front. And then I was using a laser cut table with the crack in it to validate the experience through object detection. So the object detection was performed with the faster CNN with Inception V2 architecture, pre-trained on a COCO dataset. I trained, test, and validated the dataset on the model on top of 3,000 images. And all the images were manually labeled with the label image software. And then I split the dataset into 70% for training and 30% for testing and validation. The problem with this dataset is that the majority of all of the images were just showing the fracture without any other object inside the picture and no occlusion. So I had to perform a set of augmentation to improve the robustness of the model of the object detection network. So first, I decided to add a sort of a background to these images. So I randomly pasted these patches on possible images or possible scenario that you may find in nuclear extreme environments. The problem is that since I didn't have any PNG for the images, I only have the GPG, so I had to pass the whole patch. So the problem in this case is that the network may recognize may base the object detection for the crack just on the squared gray, the gray squared patch. So in order to overcome this problem, I also randomly pasted gray flat surface of patches to improve the robustness of the model. In addition, I also created an occlusion by randomly pasting objects on top of the crack. In this case, I'm showing the screws because they are one of the possible objects that may be found in extreme nuclear power plants. And then a random set of augmentations, so horizontal flip, scale, translate, rotate, and share. So the results for the experiments are divided into offline crack detection through visual inspection and classification of fracture via tactile, so force and proximity data. In addition, I also performed 2 online experiments to validate my model with both visual and tactile data used cooperatively. So the first experiment is to, as I said before, to validate the model, so for online accuracy and detection. And the second one is actually for to investigate the time required to explore a surface and localize a crack. Because as I said before, the main problem of the tactile only approach was actually the time required to explore a surface. So when the model trained with augmented images, as you can see, outperformed the baseline model, which was trained without any augmentation set. So the mean average precision achieves around 65% of accuracy. Regarding the tactile algorithm, the model, the random forest model achieves the best results when it's trained and tested with the deformation data and the proximity data, achieving around 90 average or 90% of accuracy. So here you can see an example of the online accuracy detection. There is the camera is scanning the environment, it recognizes where the possible fracture position, sends the coordinate, the region of interest, to the manipulator, which will position and start the exploration. In this case, you can see that the first crack was indeed considered as a crack, while the second one, since it is a paper printed crack, was not considered as a crack, but was indeed a false positive from vision. So regarding the online accuracy detection, I performed 10 trials, and in these 10 trials, Vision detected 7 false positive, which are indeed the paper printed cracks, and 1 false negative, so the crack was not detected, and then 7 detected cracks. The tactile, on the other side, received 14 possible cracks location and failed only 1 case, which was with a 0.5 millimeter crack. I used, in this case, as false positive paper printed cracks because in a structured environment, a supervised environment, you may find also some, let's say, some design, something that may be similar to a crack, but it is not a crack. So maybe some markers on the wall or something on like this. The main problem with this approach are the false negative. So whenever the crack is never detected, then the location will never be explored. So this is actually something that needs to be investigated, and the model needs to be robust against the false negative. Regarding the task completion time, so the time required to explore a surface and localize a crack for I investigated and compared only for tactile and then tactile and vision together. So only for tactile, the number of scanning movements was estimated on an average of the crack geometry of the previously described datasets and their spatial frequency. So you can see that using a combination of tactile and vision to detect the fracture requires much less time than using only tactile data. It is actually, so using only tactile was requiring on average 330 seconds, while actually using the multimodal approach require around 50 seconds, so around 1 minute. So this is for the multimodal approach, but the thing is that once we have these images extracted from the object detection, then we can further analyze these images. So these images can be further analyzed for extracting, for example, the crack geometry and calculate an optimal path for the tactile expression. So applying image processing and computer vision techniques, we can find the location of the crack branches and the nodes. So in this case, for my analysis, I'm first applying edge detection, then contour extraction. I remove the outlier of the contours, and from the final image, I create a mask of it. Once I have this mask, I can develop, I can extract the skeleton, which needs to be pruned because maybe there will be like some small external outliers. Once I have this skeleton, applying Python library, which is available on GitHub, is called SKNK, if I remember correctly. You can create a graph with the nodes and edges of the skeleton. And once I have this graph, then I extract an additional graph, which is a fully connected graph. So from each edge, I calculate the middle point, and then this middle point become my next node, and then I fully connect all the nodes together. And once I have this middle point graph, I can apply minimum spanning tree to create a trajectory of for the manipulator. So each node of the graph will be explored only once, and then the minimum path from the starting node is found and explored. The experiments performed on 25 fracture. With the experiment performed on 25 fracture, it was found that the time to explore the fracture, the images, was reduced by 12 times with graph theory. Of course, these are only simulation, but then we also performed experiments with a real manipulator, in this case, a Franca-Panda robotic manipulator. So here you can see a virtual reality environment in which operator sees the camera vision and then approves for the scanning of the crack. Then these images is sent to the object detection and then to the image processing analysis, which extract in the end the motion planning for the robot. So the robot will start the exploration by following the trajectory. And in addition, also an online classifier will be added for a real-time classification of all the middle point exploration of the graph. So in conclusion, I presented a multimodal with the visual and tactile feature for crack localization and recognition, and in addition, I had the edge detection and graph theory for the motion planning trajectory. In future research, I will also develop a teleoperated model with an operator to start the analysis and exploration of the crack, and also virtual reality visual reconstruction of the explored fracture to be sent to the operator for the inspection. So thank you so much for the attention. If you have any question or if you want to further discuss this, please you can send me an email, or you can contact me to the provided email. I will stop sharing now.
Thanks a lot, Francesca.
Thank you.
Fantastic presentation. Yeah, thank you. Well done.
Yeah, I was forgetting English sometimes.
You forgetting the what?
I was forgetting English sometime.
Oh, okay. Well, no problem. Go on. Good. Anyway, yeah, thanks for that. Any questions from anyone?
I have.
Yep, I
Yeah,
see. Annabelle, please.
Thanks. No, I was curious on the false negative cases, because you actually showed that you were augmenting the data set of the images, and you were having occlusion, right? So you had the screws that were on top of the crack, and yeah. So I was wondering, is that what happens with false negatives? So those are so what happens if, for example, you have an occlusion, right? Does the camera then detect these screws and the crack underneath? And if yes, what happens if then the robot has to go to the crack to perform the tactile inspection, but then there are parts in it? So how? Yeah.
Yeah, that actually I haven't investigated it. So I try with the model with the occlusion, and it was indeed recognizing the crack underneath. But then when we did the experiment with the robot, we didn't consider any occlusion. So we just positioned the camera in the crack in the scene. But yes, that sure needs to be identified. Maybe an additional alert may be created, like if you found that there is a occlusion, or we can add an additional class in the object detection. And then whenever there is an occlusion, we need to be careful on how to perform the expression, or maybe also recognize where the occlusion is in the image, and then avoid going there and exploring that part of the crack.
Okay, so this was not an example of the false negative.
No, this was not an example of the false negative. The false negative, I don't remember because I've done these experiments in last October, I think, November, October. I think the false negative was like a 0.5 millimeter crack positioned in a specific way, but I'm not 100% sure. So also to remember that the first time that I did these experiments, it was at home, and I was using my own laptop, which has a GeForce 850M, which is 4 GB of GPU, so it's almost nothing for object detection based algorithm. So the training was taking around 4 or 5 days. So I didn't even have the time to further optimize the parameter or to further investigate the model. But now I bought a new laptop. So
it's solved.
Yeah.
Nice. Thank you.
Thank you.
Yep, thank you. Any further questions? Yep, Gitao.
Yes, thank you for a nice presentation. I really like the multi-stage approach when using first camera base to say, okay, where might be cracks, and then like a human would do, touching with the finger, is it really a crack? And then yeah, this is really a nice idea. My question was would be regarding to your training data set. You have used images of cracks. So first of all, how many images of cracks did you use? And in your augmented images, you use or cut out of your crack images and place them somewhere in the environment. And do you think it would be a problem for the recognition just to focus on the cut out shapes, like they were mostly rectangles? Yes. And yeah, that would be my question.
Oh, thank you. So to avoid the problem of focusing just on the rectangle, we also introduce full gray of rectangles, so flat surface. So the model really needs to go and further explore to recognize that there are indeed crack and not just base its knowledge, let's say, on the square patches. Regarding the dataset, I labeled 3,000 images, I think, which was really time consuming. It was like 1 week. And then after I apply all the data augmentation, I achieved around 27 images or something. The problem is that since my GPU was really bad, I couldn't use the whole 27 dataset. So I only trained and tested on a set of 3,000 images. But for sure, having more data and more images may help in creating a more robust dataset, a more robust model. Because, for example, especially with cracks, there are so many, let's say, kind of no architecture, but kind of geometries. So there may also be two cracks in the same images or multiple cracks positioned in different shapes and branches. So it's also, I found it also a little difficult to label sometimes, because maybe there was something in the images that was not a crack, but maybe was just like a deeper part of the surface, but it was not recognized. It shouldn't be recognized as a crack, but then I was a little indecisive using it as a crack or not.
So you're still, even with 3,000 images, you're still not overfitting?
I don't think so.
Okay.
No, it was not. I mean, for the loss, for the analysis of the plots with the loss in the accuracy, it was not overfitting.
Right. Yeah, thank you.
Okay. But of course, it can always be improved.
But also it would be, I think, a nice idea to implement soft robotics because, well, as I mentioned before, it's what the human would do, just look at something, make out where the region would be and then touch with the finger. And maybe it would be a nice idea to have some kind of a soft finger explorating the crack.
Yes, absolutely.
Yeah.
And also, if you have the operator, you can also, instead of using the object detection, you can also state which location of the image you want to explore, like creating some key points, let's say, and then create yourself the possible motion planning for the exploration. Yeah.
I mean, last year we had Joshua R. Smith in our workshop, and he was working with octopus tentacles, and they did some kind of similar stuff, exploring the environment. Maybe that would be cool to have some kind of soft tentacle-shaped manipulator to explore something.
Yes, absolutely. And also, if they're robust to radiation, it's even better for our research. So actually, I forgot to mention one thing during the presentation. So I know that I said that cameras are not robust in nuclear environments, but the idea is that we're just using the camera to scan the environment. So we're not continuously using it. It's not, let's say, the main sensor in our research. Thank you for your question.
Yep, thank you. Any further questions from anyone? Nope. Okay, well then I thank Francesca again and pass over to Yitao for some concluding words, I suppose.
Right, thank you. Me again. Yeah, the last session of the workshop. Thank you much for attending, Rebecca and Francesca. And we'll have our live session on 27th September, where we have 2 hours of panel discussion. And I hope to see you there for a fruitful discussion. And yeah, that's it, I think.
Yeah. As mentioned before, you will receive an email with the instructions for the uploading of the video. But apart from this, thanks again for your contribution. Was really, really nice.
Yeah.
Maybe just to add a thing that comes to my mind, we should somehow force people to look at the videos. I mean, once they have looked at it, they will realize that it was a good thing to do. But often it's difficult to convince people to actually, go there. And that would be the idea, to do that before we meet on the 27th of September. So any thoughts on how we can, push people a bit more?
Again.
First of all, maybe I should stop the recording, so you can just say bye, but not really go out. And we can further discuss. So
yeah, let's also stop.
Bye to the audience. And I will stop the recording.